Alright, hey guys, welcome to the Chemistry Club. In this series, we'll be doing AP and SAT test prep. So let's begin with our first unit, which is on the structure of the atom. So let's start with the parts of an atom. This isn't the full picture of the atom, but it's all you really need for your AP and SAT test. So we'll start with the proton, which has a charge of +1. Remember, this charge is relative to other parts of an atom. So the proton has its own charge in coulombs, which is a unit of energy, but to make it easier, we say that one proton is +1. Next, you got the neutron, which is about the same mass as a proton and doesn't have a charge. It's in the nucleus with the proton, and they chill there together. And next, you have the electron, which has a relative charge of -1, and it orbits around the nucleus. So one of the most important views of how atoms worked was the Bohr model. Niels Bohr particularly studied the hydrogen atom, and he came to a few conclusions based on his studies. One was that electrons orbited the nucleus in set orbitals, kind of like how planets orbit the sun today. The planets orbit in these circular orbits, and that's how Bohr thought electrons worked. They kept to this path and they didn't stray too far from it. And another conclusion that Bohr made was that if electrons received some energy, for example, if you passed electricity through the atom, the electron, which has higher energy, would move to a higher energy orbital temporarily. And then when it came down, since it has to release that energy to return to that lower energy state, to be in that lower energy orbital, it would release this excess energy as light. So here's an image of what Bohr thought was going on with the atom. You can see the nucleus, the black dot in the center, and around it are these circular orbitals. From this view, it really looks like a solar system, and that's a good way to visualize it. But the most important part of this diagram is the representation of the electron releasing light. You can see it goes from the second to the third level, and then as it comes back down, it releases the energy as light, which is the red wave that you see there. And this diagram is what allowed Bohr to make his observations about light. So up top, ignoring the black lines, you can see the full electromagnetic spectrum for visible light. In other words, it's like a cross-section of a rainbow. It's got all the colors that we can see with our eyes. Now the diagram on the bottom is a emission spectrum for hydrogen. So let's say if you pass some electricity through hydrogen gas, you would only see these colors. So how does this work? It's based on the fact that Bohr thought that if the electron orbitals and energy levels associated with them were constant. They were like a staircase. If an electron had enough energy, it would jump up to that energy level. It isn't this gradual increase, but more so climbing one chunk at a time. And then when this electron comes down, it releases the same amount of energy as it gained going up, because it's going down the same set of steps as it climbed before. So the height of each individual step is the same, and thus the energy levels of the two are the same. That means that if the light released when going to and from the two steps is always the same for any electron in any atom of hydrogen, that means that hydrogen only releases a few specific colors. Other atoms work this way too. A good one to remember would be neon. It releases its characteristic colors because of this property. That's just how neon lights work. It's just electricity being passed through neon gas, and neon gas giving off the specific colors of light that it does. The other nice thing about this is that what Bohr found is consistent with what we know today. It's just his interpretation of electrons that orbit the atom in circles that was wrong. So, we've talked a whole lot about how electrons can release light, but we haven't talked much about light itself. So, light itself is a wave, which in this case looks like a sine or a cosine graph, if you've done one before. It just goes up and down to from the same max height to the same bottom height for infinity. And one property of this wave is that there is a wavelength, what we would call a period with sine graphs. A wavelength is just the length of each repeating unit of a wave, or from an initial point to an end point where the function has gone through the wave and come back exactly to where it was at the initial point. And we express this in units of length. For the AP and SAT test, we use SI units, which is just System International in French, meaning that they're internationally standardized units, or more commonly known as the metric scale. We're going to be using meters and all the prefixes that go with it. And another property of light is its frequency. And frequency is just how many wavelengths can pass through a point every second. So we'll use the units 1 over seconds or simply hertz, which is just 1 over seconds. Just looks cooler. So this image shows us two waves. The one on the top has a short wavelength, and the one on the bottom has a longer wavelength. And what we see is that wavelength inversely affects frequency. That is, if wavelength has a higher number, frequency will have a lower number, and vice versa. The nice thing is that wavelength multiplied by frequency will always equal a constant, since if one is higher, the other is lower. And this brings us into our equations with light. The first is that c equals lambda v. Lambda is the Greek letter that we use as a variable. So here c is the speed of light, lambda is wavelength, and v is frequency. This is what I talked about before. The constant is c, or the speed of light. And that equals wavelength multiplied by frequency. So that's our first equation. Next up we have E equals hv, like that. And that allows us to relate the frequency of a wave with its energy, or E, which is in joules, which is a unit of energy. We will use joules more in thermochemistry. And this equals V, which is frequency, multiplied by Planck's constant, 6.63 times 10 to the negative 34th joules per second. Don't worry, you don't have to memorize that. It's just the way that we relate energy with frequency. It's just that number there that conveniently ties everything together. So, of course, for the AP test and the SAT test, we're going to be using metric or SI units, and these have prefixes. So these prefixes are consistent with all the units used in the SI system, and they're based on multiples of 10. So an example would be like the kilogram, which is 1,000 grams, or kilometer, which is 1,000 meters. So here's this chart. For the light problems, the one you definitely want to know is the nano prefix, which is 10 to the negative 9th. So you want to know how to convert meters to nanometers. And by knowing what nanometers are, which is one nanometer being 10 to the negative 9th meters, it's easier to convert between the two. So hundreds of nanometers is the wavelength for visible light, which is what the questions usually end up asking. So next up, we're going to be talking about the wave mechanical model. This is our current model of the atom, and one of the major assumptions is that electrons don't orbit the nucleus in circles, like Bohr said, but more likely they exist in regions of probability that surround the atom. Oops. So these are just areas that we've calculated using really complex math, where we can say that the electron will most likely be. We'll never know exactly where it is, but these regions give us a pretty good idea. And this ties up to the other big concept behind the wave mechanical model, which is the Heisenberg uncertainty principle. This states that you can never know the exact position and velocity of an electron at any given point in time. And that ties into the theme of the region. We simply don't know exactly where the electron is, and exactly how fast it's moving. So, the wave mechanical model defines our orbitals as regions of probability. So, now we have to name them. The first thing to know is the principal energy level. That's based on the rows of the table, which going from top to bottom are 1 through 7. And take note, we're talking about the periodic table, which is your holy bible of chemistry. And as the numbers get bigger, the orbital has more energy, right? So if we're going from 1 to 7, that's going from increasing energy. So 1 is lowest energy, 7 is highest. And after that, within each principal energy level, we have subshells. So subshells are just different kinds of orbitals that exist within each principal energy level. And these are based on columns. And one thing we can say is that every orbital, so subshells S, P, D, and F, they have individual orbitals. S is 1, P is 3, D is 5, F is 7. So there's separate different kinds within each group of S, P, D, or F, or whatever number there is. And one thing we can say is that each specific orbital within each group holds 2 electrons. So this is better demonstrated in this image. I hope this explains it a little bit better. So first you can see how the principal energy levels work. It goes up working our way down the table, right? It goes from 1 to 7, top to bottom. And within that you can see the types of orbitals, or the specific subshells, S, P, D, and F. And you can see how there's 2 elements in the S columns, 6 in the P, 10 in the D, and 14 in the F. And we know that there's 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. So that means that every individual orbital, again, holds 2 electrons. So this is what s and p orbitals look like. The s is a sphere, and remember there's only one s orbital individually. That makes sense, right? You can't change a sphere in any way to make it any different from the original sphere without moving it or scaling it. And next up we have the p orbitals, right? There's 3 of them, 1 on each axis. And remember, each p orbital holds 2 electrons. And remember again, these are just regions of probability. They are not solid orbitals in which the electrons are moving on, but they're regions in which we're probably going to find the electron at any given moment in time. So this is more of a visual representation of our atom so far. So instead of the traditional model that you're used to looking at, where the electrons orbit in circles, this is more likely what the atom looks like. So this would be something in the 3s, which would be sodium or magnesium. And you can see here there's a 1s orbital in the center, and then we go up to the 2s orbital, so those are both spheres. And then the 2p's orbitals are in that general area, and those are all encompassed by the 3s. And again, remember, these are just regions, so it's okay if they intersect, because the electrons themselves are probably never going to touch each other. Some of you may have noticed this. If we look back at the table, you will see that the energy levels of 3D are higher than 4s, energy levels of 4f are higher than 6s. So what that means is that if you look back at the table, right here, you can see that at 4s, right after 4s, we go immediately to 3D, which doesn't make sense. It's why aren't we going to 4D, right? If we're going from 2s to 2p, then why aren't we going from 4s to 4D to 4p? And that's because 4s is at a lower energy level than 3D is. So the electrons are... So it's easier for the electrons to stay at the 4s level than it is at the 3D level. So if the 4s orbital is open, then the electrons naturally just tend to stay in the 4s orbital and not the 3D orbital. And same goes for the f orbitals, right? So we go from 6s to 4f to 5d to 6p. So the f has really high amounts of energy. So it puts it down 2 rows lower. And this is sort of a graphical representation of what's going on with the D and Fs. This one only shows D, but the concept behind the F is the same. So what we see here is that it goes from 1s to 2s to 2p to 3s to 3p. That's all normal. And then it goes immediately to 4s, and then right after that is 3d. So what you can see here is the axis going up is just increasing energy level, right? So you can see that the 4s is at a lower energy level than 3d is. And because electrons always want to stay at the lower energy level, which is something you'll learn next lesson, that's why 4s is at that lower energy level and comes before 3d does. And the same applies for for the f orbitals. So in the next lesson, we'll be covering this notation that you see here on this image, which is electron configuration. Hope to see you then.